Skylon was a proposed British single-stage-to-orbit spaceplane designed to revolutionize space access. Developed by Reaction Engines Limited, it featured the revolutionary SABRE engine, capable of air-breathing operation in the atmosphere and rocket mode in space. Engineers envisioned rapid, reusable orbital flights at greatly reduced cost compared to conventional rockets. Despite decades of development, the program was repeatedly delayed and ultimately never flew. The vehicle was designed to take off and land horizontally like a conventional airplane. Its fuselage was shaped for aerodynamics across both subsonic and hypersonic regimes. Skylon promised fully reusable operations, eliminating the need for expendable boosters. The ambitious design combined cutting-edge propulsion, thermal protection, and lightweight materials in one platform. The Skylon concept originated in the 1980s as a response to expensive and limited orbital access. Reaction Engines Limited pursued an innovative solution to reduce launch costs. Their vision was a spaceplane capable of reaching orbit without staging. Initial studies focused on integrating air-breathing engines with rocket propulsion. The SABRE engine was the core innovation of the program. It could operate in air-breathing mode up to Mach 5 before switching to rocket mode. This hybrid approach aimed to maximize efficiency and minimize oxidizer requirements. Engineers believed this could dramatically reduce launch mass. Skylon's airframe incorporated advanced composite materials. Lightweight alloys and heat-resistant structures were critical for both atmospheric and spaceflight. Thermal protection systems were designed to handle re-entry temperatures without expendable tiles. Structural integrity was a key focus from the earliest designs. Funding and government support fluctuated throughout the program. The UK government and private investors provided intermittent backing. Delays in engine development slowed progress significantly. Despite this, the project maintained momentum through careful engineering work. Early wind tunnel and scale model tests informed aerodynamic design. Engineers simulated flight across a wide speed range. The design emphasized stability and control in both high-speed air and low-density altitudes. Each iteration refined lift, drag, and re-entry profiles. By the early 2000s, Skylon had matured into a fully conceptualized vehicle. Extensive computational modeling validated the airframe and propulsion integration. Confidence grew that a real prototype could be built. International interest in reusable spaceplanes added credibility to the effort. Skylon's fuselage was slender and aerodynamic for efficient atmospheric flight. Wings were swept to optimize performance at hypersonic speeds. The entire structure emphasized low weight and high strength. Designers aimed to achieve orbital velocity without shedding stages. The SABRE engine integrated pre-cooled air intake technology. Atmospheric air was cooled to cryogenic temperatures before combustion. This allowed continuous operation without overheating the engine. Engineers considered this a breakthrough in propulsion efficiency. Thermal protection was critical for re-entry operations. A combination of high-temperature composites and active cooling protected the airframe. Reusable heat shields eliminated the need for replacement tiles. Designers modeled thermal loads extensively to ensure safety. Avionics and flight control systems were highly advanced. Automated guidance managed both takeoff and orbital insertion. Redundant systems were included to mitigate potential failures. Control surfaces were optimized for both subsonic and supersonic flight regimes. Fuel management was a complex engineering challenge. Liquid hydrogen was the primary propellant. Efficient storage and insulation minimized boil-off during ascent. Propellant systems were integrated to work seamlessly with the SABRE engine. The design promised rapid turnaround between flights. Reusability aimed to reduce operational costs dramatically. Skylon was intended to carry satellites or payloads to orbit without multiple stages. Engineers believed this could change the economics of space access forever. Early testing focused on scale models and engine demonstrators rather than full-flight vehicles. Reaction engines developed ground-based SABRE prototypes to validate air-breathing and rocket modes. Wind tunnel experiments assessed aerodynamic performance across subsonic, supersonic, and hypersonic regimes. Each test revealed critical insights into thermal loads, airflow management, and structural stresses. The pre-cooler system in the SABRE engine was tested extensively on the ground. Engineers confirmed the ability to cool incoming air from over 1,000 degrees Celsius to minus 150 degrees Celsius in fractions of a second. This technology was unprecedented and required innovative materials to prevent icing and structural failure. Successful tests increased confidence in the engine's viability for flight. Scale model flight tests simulated high-speed transitions between air-breathing and rocket modes. These models measured control responsiveness and stability during acceleration. Engineers analyzed shockwave formation and temperature gradients. Data collected refined aerodynamic surfaces and control algorithms for the full-size vehicle. Prototypes demonstrated rapid startup and shutdown sequences of the engine. Engineers evaluated fuel flow, combustion stability, and thermal expansion. Each test helped optimize the complex integration of propulsion and airframe systems. Reliability remained a central concern throughout testing. Instrumentation and telemetry systems captured every aspect of experimental flights. Engineers monitored vibration, temperature, pressure, and structural loads in real time. This allowed immediate analysis and adjustments for subsequent tests. Continuous iteration improved confidence in theoretical models. The testing phase revealed potential operational challenges. Heat management during high-speed flight remained critical. Fuel consumption in hybrid mode varied more than predicted under realistic conditions. These results emphasized the difficulty of moving from theory to practical spacecraft operations. Ultimately, the prototype tests demonstrated the technical feasibility of Skylon's design. Air-breathing hypersonic flight could work in principle. The vehicle's reusability and combined propulsion systems were validated in laboratory and small-scale flight experiments. These successes, however, were not enough to ensure program continuation. Despite successful ground and scale model tests, Skylon faced enormous technical challenges. Full-scale flight testing remained unachievable due to cost constraints. The complexity of the SABRE engine demanded precision manufacturing at unprecedented levels. Funding delays slowed progress and limited prototype development. Integration of advanced materials presented ongoing difficulties. Lightweight composites needed for high-speed flight were expensive and difficult to produce consistently. Thermal protection systems required rigorous testing to withstand repeated re-entry cycles. Each innovation increased both schedule risk and overall program cost. Political and budgetary factors further complicated development. Changes in government priorities affected financial support for the program. Investors were cautious due to long timelines and uncertain returns. International interest in competing launch systems also shifted attention away from Skylon. Operational feasibility remained unproven. While laboratory and scale tests indicated potential, real-world flight conditions could not be fully validated. Maintenance, turnaround, and reliability concerns persisted. These uncertainties weighed heavily on decision-makers evaluating the project's future. Public and media attention highlighted Skylon's ambitious goals. Articles praised its potential to revolutionize space access. Yet scrutiny intensified regarding practical obstacles and timelines. Enthusiasm alone could not sustain a program facing such engineering and financial risks. Reaction engines continued development as far as possible. The team refined engine prototypes and conducted additional wind tunnel testing. Lessons learned during the program informed materials research and propulsion theory. However, the path to an actual operational vehicle became increasingly unrealistic. Ultimately, the combination of technical, financial, and political challenges led to the cancellation of the Skylon program. Despite decades of effort, no full-scale vehicle was ever built or flown. Knowledge gained, however, influenced later reusable spacecraft concepts. Skylon's story serves as both an engineering triumph and cautionary tale. Although Skylon never reached orbit, its engineering achievements influenced modern spacecraft design. The SABRE engine demonstrated innovative air-breathing/rocket hybrid propulsion. Materials research and thermal management techniques set new standards for reusable vehicles. Concepts pioneered by Skylon continue to inspire aerospace projects worldwide. The program highlighted the feasibility of single-stage-to-orbit flight in principle. While practical deployment was never realized, the design validated key principles for future spacecraft. Engineers gained valuable insight into aerodynamics, propulsion integration, and structural resilience. These lessons inform current and next-generation spaceplane concepts. Skylon's approach emphasized rapid reusability and cost reduction. By combining airplane-like operations with orbital capability, the vehicle could have drastically lowered launch expenses. Economic models for space transport now consider these parameters thanks to early Skylon studies. The vision of routine orbital flights remains a driving inspiration. Technological hurdles demonstrated the limits of contemporary manufacturing and materials. High-performance composites and precision engineering required for Skylon remain challenging even today. The program underscored that innovation often requires decades of incremental progress. Understanding these limitations is critical for aerospace development. Collaboration between government and private industry was central to Skylon's progress. Funding cycles, regulatory approval, and research partnerships shaped the program's trajectory. While cancellation prevented flight, the experience strengthened expertise in aerospace project management. Future spaceplane initiatives benefit from these organizational lessons. Skylon's story continues to capture imagination in the aerospace community. It represents a bridge between theoretical concepts and practical engineering. Students, engineers, and designers study the program as a model of ambition and technical rigor. The aircraft's legacy is educational as well as inspirational. Ultimately, Skylon stands as a symbol of visionary thinking in space exploration. Its cancellation reflects the harsh realities of cost, technology, and politics. Despite never flying, the program reshaped how engineers approach reusable, single-stage orbital vehicles. Skylon remains a testament to human innovation and the pursuit of the impossible.